Hi, folks. We're going to go ahead and get started in just a minute. Please feel free to help yourself to more of the various cheeses of various forms and drinks back there. I'm Matt Schwartz. I'm the Associate Dean of the Hal Marcus College of Science and Engineering at the University of West Florida, and I'm very pleased to welcome you to the inaugural meeting of the 2018 UWF Hal Marcus College of Science and Engineering Great Minds Lecture Series. The Great Minds Lecture Series was launched by Dean Mike Huggins, who is back there at the buffet, helping himself to pre-dinner or late lunch. And was launched by Dean Huggins to use a portion of Mr. Marcus's generous donation to bring to Pensacola and to UWF world-class researchers and innovators in the fields of science, technology, engineering, and math, or STEM. With the assistance of a multidisciplinary professor advisory board made up of Thomas Reicherzer, Tanay Kesharwani, Brad Reges, Joe Lipo, and Subhash Bagui, and the support of our wonderful staff, including Tiffany Harper and Paula Wilson, the 2018 Great Minds Distinguished Lecture Series takes a special focus to demonstrate connections between STEM research and our regional and global community, to show that discoveries made in our university research labs affect life even far from the campus gates, and that STEM innovation is an engine to economic, social, and political growth around the world. In that light, I'm thrilled to introduce Nate Lewis, whose research innovations in artificial photosynthesis technology and the development of an electronic nose, and that's real, an electronic nose capable of artificial olfaction, resulted in him recently being named a Fellow of the National Academy of Inventors, an honor that certainly demonstrates that link between university research and the public good. Professor Nathan Lewis is the George L. Argyros Professor of Chemistry at the California Institute of Technology. His alma mater, where he earned BS and MS degrees in 1977, I apologize for dating you there, before moving to another world-class institution of research, MIT, to earn his PhD in 1981. Nate started his academic career as an assistant professor at Stanford University, where he earned tenure and promotion to associate professor before returning to Caltech in 1988. His subsequent work in artificial photosynthesis and solar fuels has launched the academic and research careers of many former students, led to hundreds of peer-reviewed manuscripts, and earned recognition on both the scientific and popular press with citations by Bill Gates, Scientific American, and in Tom Friedman's popular bestseller, Hot, Flat, and Crowded, amongst many, many others. If that wasn't enough, I can, and I'm very proud to emphatically state that Nate is a STEM rock star, as illustrated by his being placed at number 17 on Rolling Stone magazine's 2009 list of the top 100 agents of change in America. And that's ahead of my personal favorite statistician, Nate Silver, and Radiohead, but behind Jon Stewart and Steve Jobs. Of course, that list was in 2009, and the person at number 1 has since been term limited out of office in Washington, D.C., so I expect that Nate has probably moved up on the list. Without further delay, please join me in welcoming the UWF Hal Marcus College of Science and Engineering Great Minds Distinguished Lecture Series speaker, Professor Nate Lewis.
Thanks. Thanks very much. I don't think I moved up on the list. LeBron James was 52 at the time. I think he's changed a little bit more in the interim. We're doing fine. Thanks so much for the invitation, and it's great to come out of the little cold here and learn about energy and climate. Let me preface this by saying that many people, including me, believe that in one form or another, energy is the top challenge for science in the 21st century. Now, when we have miracles happening in medicine and thinking about cognition in the brain, and when we have a new generation of apps and software every year, that's fighting words, right? Why should this rise to the top? And I'll spend the next hour telling you just why that is. I have three parts of this, and the reason that is because there are some undeniable facts, and then there's the future, and so to make sure that the present is differentiated from the future, they're different colored slides. So we won't confuse what we know with what we think might happen. And I teach freshman chemistry, and I know that all studies show that people can only remember 3 things out of an entire 1-hour lecture, so I'll tell you what those 3 things are. The clue here is the Stone Age. Now, you have no idea why I want you to remember the Stone Age at this point, but I'll decode it for you in less than 15 minutes. And then I'll tell you about the future, and you need to remember the number 3,000 years. And you have no idea why, but I'll tell you that number in half an hour or less. And then you need to remember the third clue, which is Willie Sutton. And even if you know who Willie Sutton was, you probably have no idea what Willie Sutton is doing in this energy talk until about 45 minutes in. And if you want to hear a longer version of this, you can get it off my website. It's streaming. I have given this talk in one form or another to probably live 250,000 people or more, and still think it's very valuable to bring out these facts in an otherwise muddied conversation, both politicized and otherwise. I'm not the only person saying this. I used to go around the country with a Nobel laureate who shared this sentiment, Rick Smalley. He said about a decade ago, testimony under oath, that energy was the single most important challenge facing humanity. Our technical journals said it. Tom Friedman says it's what our next moonshot should be. It's obvious. Universities are saying we better get going on this. It's our responsibility to lead. So there's a recognition that it's not all just having the technology and needing political will, that there are issues here that science and technology are going to have to deal with to see our way clear. Energy is so big that it needs its own units to describe it. And part of the reason that it's so obfuscating is because I think people try to make it confusing so that nobody can actually understand how much it matters. And we hear about barrels of oil equivalent and short tons of coal and cubic feet of natural gas and kilowatt hours, and no one can figure any of this out without unit conversions based on some class at the University of West Florida. On the other hand, I'm going to keep this really simple. In units everybody can understand, which are watts. Watts, a joule per second, it's a rate of energy consumption. Laptops are a few watts. 1,000 laptops is a kilowatt. That's a toaster or a hairdryer. Yeah, it's true. My wife thinks it's my big screen TV that's making our electric bill, but I know better. It's the hairdryer in the bathroom or the toaster. 1,000 flying toasters is a small jet engine. That's a megawatt. 1,000 of them is a gigawatt. That's a nuclear power plant, about. And 1,000 of them is a trillion watts, a terawatt. And that's the average electricity load consumption averaged over a year on our planet. We use about 1 terawatt on average of electricity. And you can see that just looking at this image, which I have to tell some audiences, but I'm sure not this one, wasn't all taken at once. The difference between North Korea and South Korea, the difference between the 2 billion people that don't have modern energy services and are in poverty, and there's no way to get them out without energy because we fight wars over energy. We can't get people out of poverty and can't cure disease unless we have refrigeration to get them vaccines and their ability to communicate. And Rick Smalley used to talk to church groups a lot and say, what are the top 10 problems in the world? And it would be poverty and famine and war and hunger. And then the one enabling technology that would always rise to the top, that without which you couldn't cure any of those others, was energy. But even this 1 terawatt, the 1 trillion watts, is not all the energy we consume. That's all the electricity that we get from the energy that we use to light our light bulbs. So if we add that up, it's 10 times more. In fact, it's now 15 times more. It's 15 trillion watts. So that's what the world's energy meter reads all of the time. You can't solve a problem if you're making a terawatt and the problem is 15 times that. So we need to get to grips with the scale of the problem. Now, 85% of that comes from fossil energy. Some of these slides are old, but either for better or worse, except around the edges, the picture hasn't really changed very much. And it's still true that about 85% of primary energy consumed on our planet comes from oil, coal, and gas in roughly equal parts. It's still also true that the United States consumes about a quarter of the world's energy without a quarter of the world's population. And as the other nations seek to develop, it's not going to be that way for very, very long. Actually, we hope as a goal to get billions of people out of poverty sometime this century. In addition to this 85% of fossil energy, biomass produces about 10%, but don't be fooled, most of that is unsustainably burnt. Only about a tenth of that is actually sustainably cultivated and reused crops. And then we have a little bit from renewables. It's grown somewhat in this, but still not more than a few percent of our total primary energy consumption. And then there's nuclear power. Now the aficionados amongst you will know immediately that we produce only about a third of that much electricity, but this is the primary heat content of all the energy consumed on our planet. And when you have nuclei that make heat, only a third of that goes to electricity, in the same way that when you burn coal, only a third of that goes to electricity. So this is the primary energy consumption on a fair footing on our planet in that snapshot. Well, maybe we'll run out of oil, gas, and coal, and so the picture will just change naturally because we won't have any choice. And there was a time when people were invoking Hubbert's curves and peaking oil, and during that time I was maybe a lone voice saying that's not the way it really is. The basis for that is that if you took, for instance, 1998, but it would happen again now, the consumption of oil, gas, and coal in that year, and divided by proven reserves, the amount of oil, gas, and coal that you can tell as a company you have with 90% confidence in the ground today is 40 years worth. And if you added unconventionals, it might be 80 of oil. And gas was between 60 and 160 before fracking, and coal was 200 years. On the other hand, this is not a basis to say that we're going to run out of oil in 40 years, because the ratio of proven reserves to consumption has been 40 years for the past 100 years since the day after oil was discovered. When you're an oil company or a country, and it costs you $1 million a day just to drill a well in the Gulf of Mexico, and 3 out of 4 of those are still dry, you only invest enough assets to prove out 40 years worth of reserves of oil. It makes no sense financially to keep 100 years of reserves in the bank and not produce it or get any return on your investment during that period of time. So this is not a relevant statistic as to when oil will peak or run out. What matters more is what's the resource base, what's there to be had, to be found on our planet. And that's between 50 and 150 years of oil, between 200 and 600 years of natural gas, and more now with fracking, and over 2,000 years of coal. The Stone Age didn't end because we ran out of stones. If you don't believe you like the quote, see the title to one of the chapters in Tom Friedman's book, Hot, Flat, and Crowded. That's exactly it. And the fossil energy age is not going to end anytime soon because we're going to run out of fossil energy. So I've just told you there's no problem. And in fact, the energy companies and countries are doing a fantastic job of spurring economic growth and development amongst the nations of the world based on abundant, relatively inexpensive fossil energy. It is hard to say that that is not a completely true statement. Well, I'm going to change colors of slides because that was the present. And now we have to say, well, why are you even telling me about this if there's nothing to worry about? Well, it's hard to make predictions, especially about the future. I didn't say this. Yogi Berra probably didn't say it first, even though he's quoted. Niels Bohr said it. I've got it back to Shakespeare. We can go from there. Marty Hoffert, now emeritus at NYU, wrote an important paper in Nature in 1998 that summarized some things that were said by the Intergovernmental Panel on Climate Change. But this paper is not about climate. It's all about energy. And so I have to lead you through some of those to understand what we talk about when we talk about energy demand. There's a scenario often called business as usual, and it was then decoded that business as usual, according to the IPCC, is hardly business by anybody's usual, but it's the built-in baseline assumption that we need to understand to go from there. And what they said, and what I like, is let's consider 2050, the mid part of the 21st century. And I like that for two reasons. The first is that if you're privileged to be a professor like me who teaches 19-year-olds, they're going to be about my age in 2050, and so it's not that far off the time horizon. The second is that energy infrastructure lasts by about 40 or 50 years, and so 2050 isn't 30 or 40 years away. It's at most 5 or 10 years away. We're building that infrastructure right now. And so we actually have to plan to see what that future is going to bring unless we change paths. Well, if you ask most people about energy consumption, they'll say you have to know how many people there are consuming energy. That sounds right. And so we'll say roughly there are 9 or 10 billion people on our planet by then. And that's what the IPCC said in business as usual. Well, you also have to know about economic growth, because after all, if we lived in caves and didn't use any energy, it wouldn't really matter how many people there were not using it. And it also matters what we do with our lives. And so we need the per capita gross domestic product growth, which the IPCC in business as usual said that we believe the next 50 years will be at the historical last century average, which was 1.6% per year. Now, no country, except arguably North Korea, has a policy against economic growth. And 1.6% per year globally is below most of the developed nations' targets, and certainly well below China and India, and where we need to be to bring sub-Saharan Africa out of poverty. So if we just keep it to this, the situation will only get worse if we actually have more economic growth. So let's use that assumption. And due to the magic of compound interest exponentials, these two things multiplied together, if unabated, would lead to a tripling of energy demand within our lifetimes. A tripling from 15 terawatts to 45 terawatts. But it is abated because we have saved energy per unit of GDP. And in fact, that's been going down at about 1% per year. Now, interestingly, the United States, somewhat ironically, can claim that we are leading the world at showing the world how to save energy. We can only do that because we are so wasteful that it's easier for us to save energy. And so, indeed, we are doing that, saving energy at a rate of 2% per year, whereas the global average is about half of that. And you can see why that is, because if you're a school child in India studying when you have one candle at night until the candle burns out, how much actual energy can you really save compared to the developed world? And so the global average is about 1% per year. Now, this will not be easy because due to the magic of compound exponentials, this means that if we build in this assumption, energy demand per person would be 2 kilowatts per person on average for our planet within our lifetimes. That's what that extrapolation leads. That's 5 times less total energy per person on average than what you all use today. If you were to drive a car for half an hour, that would be your entire energy budget under this scenario. You couldn't eat. You couldn't turn on a laptop. You couldn't heat your homes. That would be it. To tell you what 2 kilowatts a person means, it's still lower than the most energy efficient advanced countries, the Switzerland and Japan, by a factor of 2. China is above this line. India has a government policy to get above this line within the next decade as it brings almost 1 billion people out of dire poverty. And furthermore, to think about this 2 kilowatts per person, a 2,000 food calorie a day diet for a human is an energy burn rate of 100 watts. So humans are 100-watt light bulbs. You can think of yourself as a 100-watt incandescent bulb walking around. That's your rate of energy consumption. Well, 2,000 watts, 2 kilowatts is 20 times that, except that the embedded energy in food, the energy needed to grow the food, to harvest the food, to get it into the supermarket, and to get it into your home, and then get it onto your table, is between 10 and 20 times the energy in the food itself. Don't even think about Mediterranean olives and Trader Joe's here, right? This is just on average. Well, if I hold it to 10, then that's for 100 watts, that's a kilowatt, and I'm going to give you 2. So we're going to assume we save so much energy that on average, everybody's only consuming twice what it takes to eat within our lifetimes. Well, if we do that, then under this business as usual scenario, if we multiply how many people by economic productivity, by energy consumed per unit of economic productivity, we get how much energy we would consume. And that's quick arithmetic, and it brings us onto this top curve that energy demand will only double by the mid-21st century, 25 or 30 trillion watts. All studies show that energy will double, and if we held it constant, something the world has never done in human history, used less energy in the year than it did in the year before, nothing I'll tell you about will change. Well, I told you we had plenty of oil, coal, and gas to support economic growth for hundreds, if not 1,000 years at this rate, so it's no problem. But there is one potential problem, and that's the amount of carbon emitted to the atmosphere as carbon dioxide per unit of energy consumed on our planet. We started out with wood heating up cave people, and that's an inefficient, bad engineer because you burn a lot of wood to give her a little bit of heat to the person in the cave, and all the energy mostly goes out as CO2 to the air. We got better when we started to use coal to run our locomotives in the Industrial Revolution. That's bad chemistry, though, because coal is by weight almost all carbon. So when you burn it to make heat, you make almost all carbon dioxide. Whereas natural gas is better chemistry because it's methane, CH4, by chemical formula. So when you burn it, you make 1 molecule of CO2, but release 2 molecules of water. So you release less carbon dioxide per heat made by burning methane than you do by burning coal. And gasoline, having a chemical formula in between, is in between. These 3 things you can do nothing about because they are given by what's called stoichiometry and the heats of combustion and the laws of chemistry. And what we were on average is after we stopped being all cave people in the Industrial Revolution, the average carbon intensity, carbon emitted per unit of energy consumed, had been declining at this rate. And of course, by about the year 2000, we were in the middle because we were using roughly equal parts of oil, gas, and coal. And so the weighted average is about in the middle. Well, in addition to saving energy down to twice what it takes to eat, the business as usual IPCC scenario said that we think the next 50 years will continue along the historical trend of the last 100 years. Well, it's pretty easy to see that by 2050, that means that the carbon intensity is lower than that of the least carbon-intensive fossil fuel, natural gas. And the only way you can get to that lower than the average value, the minimum, is to have a zero somewhere in the arithmetic. I'll tell you how much you need to make this zero later, but let's just go with this, because this is what was called business as usual. In almost 30 years, we have an energy intensity based on carbon lower than that of all pure natural gas economy. Well, if we know how much energy we consume in every year, and if we know the amount of carbon emitted per unit of energy consumed, it's just arithmetic to then deduce how much CO2 will be released to our atmosphere every year under that scenario. There's no assumptions here other than these business as usual baselines. The significance of that is that brings us on to this top curve. And that even that, energy down to twice the level it takes to eat, and an economy better than that of a pure natural gas economy is not close to what it would take to reduce the carbon dioxide concentrations to the values shown on these graphs in parts per million. If you wanted to hold the carbon dioxide values in the atmosphere to 350 parts per million from the historical 280, you would have to follow this curve. That is, you couldn't burn a drop of oil, coal, or gas again on our planet forever within the next 30 years. When people hold up these signs saying 350 org, that's the scenario that they are saying that we want to be on based on that number. If you were at 450, which is the code word for a 2-degree centigrade change, because people think they can't understand scientific units and try to convert that into temperatures where there is no such conversion possible, because nobody knows precisely which carbon dioxide concentrations will lead to any given temperature changes. That would be 450 parts per million. This is 550. You have to do better by far than those two assumptions to get onto any one of these curves. Now, what do we know? We do know that historically, from ice core data, from looking layer by layer into the ice, that carbon dioxide levels year by year have been measured in temperatures from isotopic thermometers of ratios between deuterium and hydrogen, year by year, for 450,000 straight years, now extended to 670,000 straight years. Every year show that when CO2 levels have been in a narrow range of between 100 parts per million, going up or down in that range, temperatures also change that drive us into and out of ice ages. 7 straight times. We know that because of human activities, and we've labeled that carbon dioxide, we know it comes from fossil fuel burning, that the CO2 concentrations are now above 400 parts per million from the 280 parts per million that we got from our parents' over 10,000 years in the pre-industrial era. We do know that we're on track within our lifetimes to get it off of the charts. We know that even when it was only about 350 parts per million, that it's correlated with temperature changes that send us into and out of ice ages. But correlation is not causation, and therefore we cannot use this to make the robust scientific prediction of what these concentrations will bring for our planet. We do know that it's correlated year by year, every year for 670,000 straight years. So when I gave this talk to an audience that happened to have Clint Eastwood in it, I did say, do you feel lucky? And if you've seen Dirty Harry, you will know what I mean. We do know things are changing. And by the way, I need to also remind you that the Earth has many thermal time constants. So although there are predictions that say that 350 parts per million would lead to temperature rises of this or that, think about what happens to a glass of water with an ice cube or two in it that you put it on the stove and you heat it up on your gas range. It takes a long time for the temperature of the water to move until you melt all the ice. And that's the kind of thermal time constants that it takes a while to equilibrate, 30 years, the atmosphere, and then a lot longer for the oceans, and then a lot longer for the carbonate in the core and mantle of the Earth. So these predictions and correlations of what temperatures should be are going to come not now, but in a 50 or 100-year time scale, as opposed to saying, well, I don't see much yet. That is not the real issue. We do see, of course, glaciers melting everywhere. And we don't understand it. In fact, if you looked at the predictions of the rate of ice melting, here's what they were, and here's what their predictions were, and then here's the actual measurements made after that. And you can see that it's worse than the worst rate of prediction was, because we don't understand when you lubricate an ice sheet then how it will slide off as opposed to just melting in place and then release that water into the oceans. We do know that there was a massive release of carbon dioxide in the Permian era, 230 million years ago. We know it was not as rapid as the release that we're causing now by consuming fossil fuels. We know that CO2 concentrations went up to 550 parts per million, where we will take it. We also know from the fossil record that 90% of the species then on Earth could not adapt and went extinct. We, of course, have no way to know that that would happen again unless we do the experiment. No matter what you say about carbon dioxide in the atmosphere, anybody that's ever put soda water into a drink knows that when you add CO2 to water, you make it acidic. The pH of the oceans is lower than it has been in 4 million years and probably in 20 million years. Here's a map from the ocean chemistry just of making water acidic by bubbling carbon dioxide through it, of historically where the pH and temperatures have been appropriate on a log scale to support coral reefs. That's at 280 parts per million, the atmosphere we got from the 10,000 years of pre-industrial era equilibrium. Here's that prediction at 380 parts per million. Here's that prediction at 450 parts per million. And here's that prediction at 550 parts per million. So if you don't feel so good about leaving that legacy, then you want to do something about this. And it's also true that I need to code that second number. That second number I gave you, anybody remember what it was? 3,000 years. If you quit cold turkey when you get to 550 parts per million of CO2 in the air, it takes between 1,000 and 10,000, and a good number is 3,000 years for it to come back to the climate and atmosphere that we got from our parents. The oceans take 2 million years. We know this from volcanic eruptions. So we are doing an experiment that is essentially going to change the chemistry of our planet for a time scale comparable or longer than recorded human history. I never told you what the consequences of putting that amount of carbon dioxide in the air would be, because for that you need a climate model. There are 6 major climate models. They differ from each other. That means we know for sure at least 5 of them must be wrong. Furthermore, climate models are the averages of many different paths because we don't have enough data to know what all the cloud cover was for the last 100 years over the entire Earth to initialize these models or calibrate them. And we're not going to have that data before we have to predict the climate in 2050. And I'll make the only solid prediction of when we will be able to predict the climate in 2050, and that's when we open our door on January 1st, New Year's Day on 2050, and look outside. This is not about sound science and proving or disproving with red teams and blue teams that are in the news now what we know. It's all about what we don't know. Well, if you don't feel that the risk calculus is such that you would like to be witting participants in this big chemistry experiment with our oceans and our air, which may not be bad, but we won't know until we get there. And we also know there will be winners and there will be losers. When the amplification of the hydrologic cycle, of the only robust physics-based prediction of what would happen to an increased CO2 level happens, some places will be more conducive to having crops, some places will be less. Regional effects are even more difficult to predict than global ones, which we can't predict at all, really, now. And so we can't say who the winners and who the losers would be, nor do we even know the sign of the effect. So we cannot do a cost-benefit analysis on this and decide what the net present value is of the planet. When you come to a fork in the road, you just have to take it. Unfortunately, we pay decision makers to make decisions in the face of partial information because anybody can make a decision in the face of total information, and we are not fortunate enough to be in that situation in this instance. Well, if you looked at business scenarios, at that business as usual, now I get to tell you how much was built in to get that average lower than the least carbon-intensive fossil energy. And to do that, you needed 15 trillion watts of carbon-free power. If you wanted to hold CO2 concentrations constant, because it lasts so long, you have to get it all from carbon-free power. Because you can't put up any more, it just adds to your debt that you're not paying the interest off of. By any measure, you need to stabilize CO2 concentrations, if that's your goal, to make as much carbon-free power within our lifetimes as all the oil, coal, gas, and nuclear power we make today combined. You cannot solve this problem by making 1 trillion watts worth of power if we're using 15 trillion watts of power. The arithmetic, cruel as it is, says the only way to get to zero is to make it all that way. And so when you see goals of 20% reduction or a 50% reduction, what do? If it's going to double and you're going to reduce it by half, that's going to make emissions constant. If you make emissions constant, then it only takes another 10 years delay to get to those concentrations than you would have done otherwise. You still get there sooner rather than never. That's the problem. Well, this is a risk problem. It's a risk of either doing the experiment or not, and of deciding to pay a penalty in cost, given our current environment where it is free to emit carbon dioxide into the air. And there's another assertion that we don't have all the technology we need, and this is not just about political will. We have to be on the ball as scientists and engineers to help lay the groundwork to get this to succeed if you believe that's the only acceptable outcome. Now I've switched slides again, because now I'm going to go back to some truths, not the future, and tell you about where you can get all that power from. Because 10 trillion watts is not a tiny number. And people try to say, well, today you can feel good. Read Tom Friedman's book, 100 Ways to Save the Earth. I felt green by saving a watt with a nightlight at home. Well, what if everybody did that? How much would you really save? Not very much. And on and on and on. We got to figure out where we can get 15 trillion watts worth of power from. And there aren't that many places on our planet that the physics say you can get all that much energy. So let's be honest and figure out where they are. Well, the only proven technology that we now have that can scale to those levels without emitting carbon dioxide is nuclear fission. Now, I'm personally not against or for any energy source, including nuclear power. On the other hand, if you tie one arm behind your back, you make life even harder trying to see your way clear. And so it's not clear that if you want to maximize your chances of success, that you don't play as many possible cards as you have in getting to the goal. But it's not so easy. If you remember that second slide in units, I told you the nuclear power plant made 1 billion watts a gigawatt. And that's the size they're built where they can be built safely. If you're trying to confine that heat and radiation and you want 10 times more power out of it, we have no materials that can do that. And so they're miracles of modern engineering, and they make 1 billion watts compared to your 1 watt laptops and 1,000-watt toasters. But we need 15 trillion watts within our lifetime. So quick math says between now and 2050, there aren't even 1,500 days. And that means you need to be building more than a new nuclear power plant a day, every single day, from now until 2050, if you want to get that much power from nuclear fission. That's what you sign up for. If you say, I want to get to a zero carbon emissions economy and stabilize carbon dioxide concentrations and hold something even close to 350 or 450 parts per million, and you want to do it with nuclear fission, you're saying, I'm going to build a nuclear power plant every single day for the next 40 years somewhere on our Earth. And by the way, since they only last 40 years, then you'll have to replace them, so you're going to build one forever, every day on our planet. Well, there's not enough uranium to do that. You may need uranium-thorium cycles. It turns out you can get it from seawater, but in order to get it from seawater, you would need kind of like 3,000 Niagara Falls is running all the time because it's only a nanomolar, it's only a part in a billion in seawater. And so, at $5 a watt, it only requires kind of $50 trillion. And by the way, no nuclear power plant in the United States has ever been built on time or on budget. Doesn't mean we couldn't do it in principle. China builds them cheaper, but they have less safety standards also, and so there's a trade. Well, there's a second way. Continue to burn fossil fuels and take that carbon dioxide, instead of letting it go into the air, what starts in the ground ends in the ground, and bury it somewhere. Now, there's only really one place buried big enough. You could put it in oil and gas reservoirs where it will stay for millions of years because, after all, natural gas was trapped there for that long. On the other hand, there's not enough volume to put all of our CO2 junk in there for very long. You can put it in the underground aquifers, in the underground brine, where there's about between 50 and 150 years worth of capacity. So it could buy us a century worth of time to do that, provided that they don't leak. If 1% of it leaks after 100 years, then what's coming out after 100 years of doing it is the same as what you started to avoid in the first place. So these reservoirs can't leak at 0.1% a year on average for 1,000 years. And you're going to have to write an environmental impact report within the next decade certifying that we know, and every geologic aquifer is different. Some have cracks, some have water transport. We know when you put subsurface CO2 down there, you make a lot of Perrier, and we could export that to the French and fix our balance of trade problems. And the problem with this was the United States' program was called the Future Gen, and the word future was always in its name. It never became present gen. And so we have very little experience at understanding whether or not we can actually put CO2 into the subsurface in these enormous volumes and keep it down there for a time scale of 1,000 years with essentially none of it leaking. And we need to understand subsurface science and technology if we're going to do that. And we need to be doing the R&D to see if that will work. Well, if you're not burning fossil energy, and if you're not using the power of the atom from nuclear, that brings us to the only other options are the natural renewable resources on the planet that we live. And there are a few of them commonly mentioned: hydro, geothermal, wind, ocean, solar, biomass. In the longer version of this talk, I'll go through that analysis, and you can find that online. I'll just give you the short version now. Hydroelectric's great, except that if you look at all the kinetic energy and potential energy in every river, lake, and stream on our planet combined, it's only worth 4 terawatts. But you can't technically dam up the Hudson River. The Yankees have to find a new place to play. And by the time you're all done with that, there might be 0.9 terawatts to be had, and we've already installed 0.6. You can't get 15 out of that stuff. What about the heat of the Earth? Well, it's well known what the temperature at the core of the Earth is and what the temperature at the surface is, plus or minus 30 degrees Fahrenheit today, but we know it on average. And that means you can calculate from the thermal conductivity of the Earth what the heat flux is. And the sustainable heat flux at the surface of the Earth is 57 milliwatts per square meter, which means if you covered all land on Earth with 100% efficient heat engines, don't exist by the laws of thermodynamics, but forget about that, you would still only get 10 terawatts. The heat of the Earth isn't close to what humans' thirst for energy is based on geothermal energy. Not even close. If you look at the wind, but you do it right, there are a lot of studies saying what the wind energy potential is that take a fast-spinning wind turbine at a very high wind speed place and then assume you did that everywhere. Well, obviously, if you're a windsurfer like I am and you get behind a sailboat with a big sail, you know I don't get that wind anymore because that sailboat just took it all from me. And that's what happens in farms of wind turbines. When you're downwind enough and each wind turbine is taking 40% of the kinetic energy out of what's hitting it, there ain't much left downwind anymore. And this works between Kansas and the next state as much as it does between me windsurfing and the sailboat, just on a different scale. So when you conserve energy in the wind field, it's pretty easy to show that there's a few terawatts to be had. Wind is the fastest growing renewable. We should do it where it makes sense, but it's not going to get us 15 terawatts. And it's certainly not going to get us 15 terawatts on demand either. Here's a 10 terawatt line. Here's the energy in all the ocean tides, waves, and currents on our planet combined. Forget about it. It's not close. Biomass. You take 50% of all cultivated land on Earth, you might get a terawatt of energy out of that based on net primary productivity of plants. And not even thinking about the food for fuel trades that we have now. Now, this could be an important terawatt because without a liquid hydrocarbon fuel that comes from fixation of carbon dioxide by biomass in photosynthesis, there ain't no such thing as a plug-in hybrid airplane, and a Prius doesn't fly as fast as an airplane, and you would shut down global commerce because we need a way to power our aircraft, our trucks, and our ships. And liquid transportation fuels are basically it for now, for a long time. So ways that can make them sustainably, even if they can't solve the whole problem, are critically important. Biofuels in their advanced form is one, and other ways to do that I'll tell you about are another. I want to skip the biofuels now, except to say that they were the darling poster child of technology, but it was obviously before its time because they mostly fizzled. 25% of the corn in the U.S. in 2007 was used to provide 2% of our transportation fuel, and that didn't stop us from passing a law that said we had to do 10 times better than that by 2017. Because quick arithmetic says that that would have offset 20% of our transportation fuel by using all of the corn in the country, plus some, by last year. That's the difference between energy policy and energy politics, right? There's a big difference between the two. But there is one big number. Remember my third clue? Anybody remember that third clue? Willie Sutton. Does anybody here know who Willie Sutton was? Good. Look, if you look at the energy in the sun, there's 120,000 terawatts hitting our surface, hitting the top of the atmosphere. And we need 10 or 15 out of 120,000 terawatts. Nothing else was close. Willie Sutton was the bank robber that when they asked him said, "Why do you rob banks?" And he said, "Because that's where the money is." He says he doesn't actually say that, but that's what Wikipedia says. For our purposes, it's good enough. This is where all the energy is. There's nothing else that's even close. Photosynthesis, the source of all oxygen in our atmosphere, every day is worth 90 terawatts, and we need another 10. But unfortunately, you can't get those 90 because it's in what's so-called detailed balance with respiration. Plants both consume CO2 and then re-emit it as they both consume and then emit oxygen between day and night as part of their balanced part of steady state in the biosphere of our planet. And this is why afforestation, planting more trees, is good but is limited because we already have a certain steady state height of carbon sequestered in trees. If you plant more trees, you basically increase the amount that's sequestered, that's stored, until you reach a new steady state, and then you don't do anything anymore. So you have a transient good feeling about it, but at steady state, you can't really pay the piper to keep eating more and more CO2 up that way because you have a limited carrying capacity of the beer. If you had 10% efficient solar panels, as a calibration, the area is not small, much bigger than the area you'd have to cover in nuclear power plants, but much smaller than what you'd have to do to get biofuels because they are very inefficient energy conversion machines. Less than 1% of the solar energy is used to be stored in the fastest growing crop. But we got a lot of land for crops on our planet, and the sun's a big constant, and so we can make ends meet that way. But this shows you how much land you would have to cover at a representative mid-latitude, not in Arizona, and you would never do it this way, to just give you a feeling if you wanted to power the United States forever. Well, there's some bad news about this. It's not equivalent to the nation's interstate highway system. It's more like all the roads. And to be fair, if you needed a new nuclear power plant every day, you need 1 million solar roofs every day if you're going to get this much land covered between now and then. The good news is I've given this talk to over 250,000 people, and I've never met anybody that actually lived there. How about this audience? Nah, so we wouldn't miss it. Just cover it up. Be done with it. It's a joke. Here's 6 3-terawatt boxes. You know, this powers our Earth forever. Oh, there's only a few little problems. One is there's not enough money to do that in the world. Because at the cost of current solar panels, they just cost way too much compared to what we're used to getting energy for in terms of not just electricity, but actual joules per dollar of energy. Electricity is expensive energy because we burn fossil fuel inefficiently to make electricity, so you know it costs you 3 times as much at least per joule to pay for the electricity as it did to pay for the natural gas that you burnt to make that electricity. And we need to make energy cheaply here, not just electrical energy. We have to get this stuff down to where it costs about as much as newspaper or carpet, because those are the only things that we make in enough volume to be able to roll carpet out or paper 1 million roof equivalents every day for the next 40 years. It can't be panels. It can't be having to pay installers. Nobody ever counts the energy that the installer needed to drive to the site to work to offset the amount of energy that the panel made. And at some point, it's not going to be a winning battle anymore. We're going to have to pay as much energy to put up the panels as we're going to get back. We've got to have a totally different form factor for this stuff. Like maybe solar paint. That'd be pretty cool. And there's nothing in the laws of physics that says that you can't do this, that you can't fool particles into thinking they're a single crystal and getting the electrons to hop from particle to particle instead of stopping and making heat instead. And so why should we have to pay to make a brittle single crystal solar panel working at maximum efficiency but taking maximum energy to install and minimum convenience instead of being able to just paint our houses or paint our areas with this cheap stuff that works just well enough to get us by? Be a good thing for scientists to do. Oh, there's one other problem. President Ford said it. He was the president. He said, solar energy just doesn't come in overnight. He should know. He's the president. That was right. I like to say it as, he that cannot store shall not have power after 4. Much more poetic. Photosynthesis is inefficient. It would get a D- in an engineering design class. Only 1% of the total sunlight is stored in energy from the fastest growing known crop. But it stores it. Solar cells make electricity, and there's no way, since Edison observed this when he invented electricity, to store massive quantities of electricity. And chemical fuels are the best way, we now know, to pump and store electricity around as energy and then burn it when we use it. People say the grid doesn't store anything. Not true, because it's all the natural gas, coal, and oil that we use to make the electricity is where all the energy is stored in the first place. It's true that batteries can't store energy very much because they carry both their reactants and their products, and so they're low energy density and expensive per unit of energy stored by a lot compared to getting it from chemical bonds. So why don't we take the sunlight and just make stored chemical fuel in the first place? But if we're doing it, we don't build aircraft out of feathers, even though birds use feathers to fly. We build aircraft with jet engines because they fly faster and longer, even though we're inspired by photosynthesis to take the sun and make chemical fuel. What if we did that 10 times more efficiently and made a fuel we could use in our infrastructure instead of this lignocellulose stuff? That sounds like a really good thing for scientists to be doing, to trying to beat nature at its own game and to take the biggest energy source we have, the sun, and to store it directly in chemical bonds that then we can pump around and use for whenever people want it, wherever they need it. Well, actually, that's exactly what my research is about. If you want to hear the technical details of that, then you can come tomorrow to when I talk about that. Let me say that that is a missing link in our energy system. We know how to take sunlight and make heat, low-grade heat to heat water, but you can't store that. We know how to take sunlight and make electricity, but you can't store that. We don't know how to beat nature at its own game cost-effectively and make sunlight into fuel that we can store. And equivalently, we don't know how to take clean electrons or low-carbon electrons from even nuclear power and make it into chemical fuel to run our transportation systems in a carbon-neutral way. And those are all related science. So let me end up by saying that I'm going to come full circle here. We need more energy. Nobody doubts that, because that's what spurs economic growth and human development. and is going to pull people out of poverty and is going to keep a civilization alive and thriving. Energy efficiency is absolutely needed to make this problem from impossible to just darn really hard, but not impossible. But don't be fooled, because no amount of saving energy ever turned on a light bulb. No amount of saving energy ever put food on somebody's table. You have to save energy to hold it where you only need 15 terawatts or 30 terawatts instead of 45, but you can't get it down to nothing unless you make as much carbon-free energy or more as all the energy we make today on our planet within our lifetimes. That's the cruel arithmetic. The case for doing that while not making CO2 is not scientifically proven. It's a risk analysis of, do we want to do the experiment and not know the outcome and not be able to reverse the effects for a time scale of millennia or longer? This is not what is in the public, but this is as far as the science will let us go. There are only three options. One is burn fossil energy, but don't let the CO2 into the air. Two is build a whole lot of nuclear power plants. And the third is, although you can have wind and hydro and other things as part of a mix, you can't do it without exploiting the big card on the table, which is the sun. And you can't do that in a system without finding a way to store it. And the best way to store massive quantities of electricity other than the nucleus of an atom is in a chemical bond. So it seems to be reasonable that that's something we should be trying all out to do, to turn up enough options to find our way to see it clear. The policy changes, I haven't talked much about policy, and I don't like to talk much about policy because this is a very politicized subject, and I'm a scientist, not a policymaker. But it does end up really being answering one side or the other two questions. One, is this something that we can afford to do? Because it will cost money. When you're taking concentrated energy, fossil energy, out of the ground and just burning it, that's got to be cheaper than taking diffuse energy from the sun or the wind and trying to concentrate it and then harness it and then direct it through wires and do something with it. So although there are niche markets now when, because of pricing, solar and wind can be favorable, over the long time scale, it's going to cost money. And maybe we decide to say that it's something that we just can't afford to do. The other side of the question is maybe it's something that we just can't afford to fail. So we have to figure that out. And there's no way to know how much it will cost unless we do it. And there's no way to know whether we dodged a bullet or not unless we don't go there. You can't justify this based on full information, based on an average performance of an investment. We get to do this or not once. So the question is, do we actually come to grips with that? Do we actually come to grips with the fact that this is going to take a commitment, that it's not going to be easy, and we shouldn't feel good that we're on a glide slope, but you got to start if you're going to see your way clear, and you can start in 10 years from now, because I said that 10 years ago, that we only had 10 years before we started to be doing this stuff, and that was 10 years ago. We're pretty close to the end decision point by where we either get our feet off the gas and on something else, or let nature, that has all the heavy hitters in this game, bat last and see what we did.